Hi class, this is a video on blackbody radiation and how to use something called Wien's law, which we have a couple of problems on in our Chapter 5 homework. Blackbody radiation is the term used to describe the type of light or other form of electromagnetic radiation which is emitted from an object due to its temperature. And here are some examples of blackbody radiation. This is a star, I believe. Yeah, this is a photograph of the sun for sure. There are no other stars for which we could take a photograph like that because they're too far away. Also, when you talk about old-fashioned light bulbs, which have a filament, as opposed to more modern compact fluorescent or LED lights, but the old-fashioned type of light bulb just had a little metal wire made out of tungsten in it, and it got hot and starts to glow. Or an electric stove or hot plate or electric heater, any of these devices where there's a heating element that you send electricity through and it gets hot, and once it gets hot enough it starts to glow, and in fact you can see the red light that it produces. The light from all of these objects occurs just because these objects come up to a sufficiently high temperature. Very quickly, in dealing with blackbody radiation, or really any time we deal with temperature in science, we almost exclusively use the Kelvin temperature scale. We don't use Fahrenheit or Celsius, and we're not going to have to learn how to do these conversions. We'll always get the temperatures in Kelvin, but I just want to make sure you understand the importance of this. The main reason that we do not use the Celsius and Fahrenheit temperature scales is because they go negative. When you talk about sub-freezing temperatures in Celsius, that goes negative. And if it gets sufficiently cold in the Fahrenheit scale, it can also go negative as well. And both of these, this is a big problem in science when you're using temperatures. You don't want to use a temperature scale that goes negative. It turns out that there is an absolute lowest temperature that you can bring an object to. We call that absolute zero. This is the temperature at which the atoms and molecules that a substance is made of would come to rest if it ever did achieve this absolutely lowest temperature possible. So we use that as the 0 point of our Kelvin scale. And just looking at some of these example temperatures, body temperature, which is 98 degrees on the Fahrenheit scale, that's around 310 on the Kelvin scale. And water boils at 100 Celsius or 212 Fahrenheit, that's 373 degrees Kelvin. And here we go, surface of the sun is 5,800. We're actually in this video going to learn where this number comes from. When we talk about blackbody radiation, and you should certainly read about this in Chapter 5 in the book because it's going to be very quick treatment of it. Again, this is the light that's emitted by a glowing object due to its temperature. And the way that we can really understand blackbody radiation is by looking at something called a spectrum. And this tells you how bright the object is, so how much light it's emitting as a function of its wavelength. So at each wavelength, these curves, these are called blackbody curves, these curves tell you how much light the object is emitting at each different wavelength. This is in the infrared. These are infrared wavelengths. This is the rainbow from red, 700 nanometers, down to violet, around 350 nanometers, and then into the ultraviolet. And these curves are for objects at 3 different temperatures, 4,500, 6,000, 7,500. And you notice that as you increase the temperature of an object, it emits more light at all wavelengths. But you also notice that the particular wavelength that the object is emitting most of its light at, it shifts from longer wavelength to shorter wavelength. So the higher the temperature, not only is it emitting more light at all wavelengths, but the particular wavelength at which its spectrum peaks, or at which it's emitting most of its light, that shifts to shorter wavelength. And so this is what we're going to be studying when we talk about Wien's law. And we call this wavelength, we call it lambda max. Lambda max, I don't know if you can read it right there, but so that's the wavelength of maximum emission. Here's Wien's law right here. It simply states that for a black body, as long as you're using the Kelvin temperature scale for your temperature, you can just take this number 0.0029 and you can divide it by the temperature in Kelvin, and out pops the wavelength of maximum emission in meters. And so it's going to just tell you what this wavelength is depending on the object's temperature. We can also take this number 0.0029 and we can express that in scientific notation. So that's 2.9 multiplied times 10 to the negative 3. 10 to the negative 3 is 1,000th. So this is the same thing as 2.9 divided by 1,000 right there. These are the same numbers, just that's in scientific notation. So here's an example. When you turn on an old-fashioned light bulb, that filament gets up to around 3,000 Kelvin. So that's its Kelvin temperature of the tungsten light bulb filament when you turn on an old-fashioned light bulb. We can calculate what lambda max is by just plugging it into Wien's law right here. So you take 0.0029 divided by 3,000. You can plug that in your calculator, or you can first convert that number to 2.9 times 10 to the minus 3, and you can convert 3,000 to 10 to the third, and then you do 2.9 divided by 3, so that equals 0.97, and then it's going to be times 10, and you remember the rule, you take the top exponent minus the bottom exponent, so you have negative 3 minus 3, that's negative 6, and as long as you put the temperature in Kelvin, the wavelength of maximum emission comes out in meters. And so this is the wavelength in meters, and you'll remember from previous videos that 10 to the minus 6 meters, we call that a micrometer. We could also express this wavelength of maximum emission in nanometers, in which case we go back to our answer right here, and we need to change this exponent to negative 9. So down here, here's the answer, 0.97 times 10 to the minus 6. We can change this to 10 to the minus 9. We're making this part of the number 3 powers of 10. So 3 powers of 10 smaller, and going from 10 to the minus 6 to 10 to the minus 9. So we need to make the other part of the number 3 powers of 10 larger. So we move the decimal place 3 spots to the right. So the 0.97 becomes 970, and this turns into times 10 to the minus 9. Anyways, after all of that, these are the same number. It's just we've shuffled them around a little bit, and now we have 10 to the minus 9 meters, and that's what a nanometer is. So this is 970 nanometers, which that is infrared, because you might remember that red light has a wavelength of 700 nanometers. This is longer, therefore it's infrared light. And here's a cartoon of the spectrum of an incandescent light bulb at 3000 Kelvin. This is the wavelength in nanometers. This is how bright it is. And as we calculated, the wavelength of maximum emission is at 1,000 nanometers, which we could also say is a micrometer. And so this is where the light bulb is putting out most of its light. And this is not what you use the light bulb for, unless you're using it as an infrared heater. You're using the light bulb to produce visible light. And so this is all the visible light you're getting out of the light bulb. This is all of the total forms of light that the light bulb is producing, and this is where your energy is going. Your energy is going into all of these various forms of light, and all you're getting is just this little bit of visible light. So that's, this is the scientific reason why these light bulbs are so inefficient, is because they're primarily producing infrared light, whereas their purpose is to produce visible light. And so that's why you see them, for the most part, being phased out and being replaced with much more efficient LED and compact fluorescent, and perhaps in the future there will be other technologies to produce light from electricity. But this is, it looks nice. It produces nice, natural-looking blackbody radiation, but it wastes most of its energy. Again, unless you're using it as a heater, which you could, in which case it would be a perfectly suited device. Okay, I'm going to post a second video on blackbody radiation, and in that video, we're going to do another calculation with Wien's law. So I will see you over there.